Hello everyone and welcome back. Now, in the previous two lectures, we were talking specifically about optimization problems when you only have a single independent variable, right? That's single variable optimization. Now, a lot of the time, one encounters multiple independent variables. I'm going to walk you through an example in this lecture. The problem is that things get a little bit more complicated. Right? And you should probably already understand this because if you've gone through a multivariable calculus course, you know that concepts that were relatively simple for single variable calculus, even things like the derivative, become a little bit more complicated when you have multiple independent variables, right? Everything turns into partial differentiation. Well, in this case, in this lecture, we're going to walk through a very, very simple example. And as we sort of progress through the next few lectures, we're going to step up the complexity and show how we can handle slightly more complex versions of multivariable optimization problems. Now, what I would like to emphasize right from the beginning is that not all optimization problems with multiple independent variables can be solved, and not all of them have a simple prescription. I can't just tell you this is a grand unified theory of how you should be approaching all of these. What I'm going to do is give you some tips and tricks and some techniques that can help you along this journey, but I do want to emphasize that this isn't going to cover everything, right? We can only cover the things that we can do well and we can do efficiently. This is very much an open area of mathematical research dealing with sort of complex and intricate versions of these problems. But like I said, we're going to focus on the basics for now, right? And the first thing that we're going to do is we're just going to solve a very simple optimization problem in multiple variables. So let me give you the following example. So I'm going to read it out for you. If you want, you can turn on the closed captions for the video and you can transcribe it. But let me just tell you, okay? So you can imagine maybe I work for a color TV manufacturer, okay? And I'm planning to introduce two new products. Okay, so I want to introduce a 19-inch LCD flat screen with a manufacturer's suggested retail price of $339. Okay, and I'm also thinking about introducing a 21-inch LCD flat screen with a suggested retail price of $399. Okay, so I'm going to put all these numbers together for you in a moment, so bear with me. Now, if I wanted to produce one 19-inch TV, it cost me $195. But if I wanted to produce a 21-inch TV, that would cost me $225. And it would also cost me an additional $400,000 in just fixed costs to even produce TVs. Okay, now, selling TVs is a competitive market. And so that means that the number of sales per year will affect the average selling price, right? If I can sell lots of them, then I can sell them for a little bit more and still, or sorry, a little bit less and make a profit. So here's what I estimate. The average selling price drops about 1 cent for each unit I sell. Okay, so I can bring down the price by a penny every time I sell a unit. Okay, furthermore, sales of the 19-inch set will affect sales of the 21-inch set and vice versa, okay? So if I'm selling more of the 19-inch sets, then I'm not selling as many of the 21-inch sets and so on. So it's estimated that the average selling price for the 19-inch set will be reduced by about 0.3 cents for every 21-inch set sold, right? So I'm selling too many of the 21-inch sets. I want to sell a few more of the 19-inch sets, so I bring down the value. Same thing. The 21-inch set will decrease by about 0.4 cents for each 19-inch set that I sell. Okay, so that's a lot of information. Now, let's take that 5-step method approach, right? So the first thing I want to do is ask myself a question. How many of each sets should be produced to maximize profit? Okay, well, that means that I would like to move on to sort of talking about the variables that are going to be involved with my model. So let's let S equal to, let's say, the number of 19-inch sets. So the number of 19-inch sets made. And let's do T to be the number of 21-inch sets to be made. Okay? Let's let little p equal to the selling price for a 19-inch set. Of the 19-inch. And let's let little q equal to the selling price of the 21-inch set. Okay, let's keep going. Let's let capital C equal to the cost of producing the sets. So the cost of production. Let's let capital R be the revenue from the sets. And let's let P, big P, capital P, the one that we care about, just like in the pig example, the profit from selling them. Okay, so now we've defined all of our variables. Now, it might have been a sort of whirlwind for you when I announced all of the specifics of the problem, but we can take those specifics of the problem and we can figure out how all of these things relate to one another. Okay, so the first thing here is that little p, so this is the selling price of the 19-inch. This is going to be a base price of $339. But it goes down by a penny for every set that's sold, so minus 0.01 s. And it also goes down by 1/3 of a cent every time there is one of the 21 inches sold. Okay, so we can do the same thing for Q. Their base price was $399. They go down 1/4 of a cent every time a 19-inch is sold. And we reduce the price by 1 cent every time we sell one. Okay, well, the revenue is going to be the selling price of the 19-inch against the number of 19 inches sold, so P times S, plus the selling price of the 21 inches times the number of 21 inches sold. Then the cost of production, we said there is a $400,000 base rate for producing these things, just right off the bat, right? That could be employee salaries, it could be just opening the factory, whatever it happens to be, $400,000 base price. Plus 195S, so $195 per 19-inch set that's made, plus 225 per 21-inch set. And this all goes together to make one heck of a profit function, okay? So the profit function is going to be the revenue minus the cost, which we can put all of this information together. And let's take a look at what it's going to be. Okay, so it's going to be P times S, so 339 minus 0.01 S minus 0.003 T, all times S, plus Q times T, so plus Q, which is 339, and then minus 0.004 S, and then minus 0.01 T, and that's all times T. And then minus the cost, which is 400,000, and then plus 195S plus 225T. So it looks ugly, right? But it's not really that bad. I want you to notice that it's really just a quadratic function of S and T. That's it, right? You can clean it up if you want to. You can put it into, anything, any sort of simplifying program you want. You can use Maple or Mathematica or whatever it is, Wolfram Alpha, if you want to clean that up. I'm going to leave it like this so that you can really see that this is, you know, the 19 inches plus the 21 inches minus the total cost. Now, what is the point? Well, the goal is to maximize P of S comma T over the set S, which is defined as S greater than or equal to 0 and T greater than or equal to 0. All right, so this is a piece that comes with multivariable optimization. You typically have a set that you need to optimize over. Now, in our case, we're optimizing over the first quadrant of the of R2 of the real plane, the Euclidean plane. So this is a relatively simple object, right? But what we'll see in the coming videos is that the regions that you want to optimize over or maximize over can often be very complicated. And that's typically where the complexity of the problem comes in. Okay, so for now, we're in nice territory. This is a nice square, sort of infinite square domain. Okay, well, the question is, how do we maximize, or how do we find maybe the critical points of a multivariable equation? Well, critical points of P when, now you might have to remember a little bit of your multivariable calculus, but it is when the gradient, so this upside down triangle or delta operator, is equal to 0. Now, what is the gradient? This is the same as the partial derivatives with respect to each variable. Okay, so the partial derivative with respect to P and the partial derivative with respect to T. So this is really similar to what we did with single variable optimization, right? Now we just have more derivatives that we can set equal to 0. So we just set them all equal to 0. Now, let's take a look at what this yields. Okay, so if I take the partial derivative with respect to P, or sorry, of P with respect to S, this is going to give me 144 minus 0.02 S, and then minus 0.007 T. And similarly, I have a partial derivative with respect to T. I've got 174 and then minus 0.007 S and minus 0.02 T. So very similar here. Now, what you'll notice is that this is a system of linear equations, right? I need to solve for both S and T because I need both of these things equal to 0. So you can go ahead and do this. I'm going to leave that for you to solve. In fact, S is going to be equal to 554,000 divided by 117. So just in case, if you want to bring your calculator around, that's about 4,735 19-inch sets. And T is going to be 824,000. So I'm going to leave them, I just want to leave them as fractions so that they can be exact for you. But of course, you know, we actually want real numbers here. So in this case, you get 7,043 21-inch sets. Now in this case, this is going to give you a local maximum of your function. How do I know that it's a maximum? Well, it's a critical point of something that is quadratic in S and T, and it has negative leading values in all of the quadratic terms, right? But in general, you need to check that this thing is actually a maximum. Now also, at the critical point, so I'm going to call it CP for critical point, that is when the gradient's equal to 0, that's exactly these values right here. We have the profit is equal to 500 and 53,631, and I'm rounding up to the nearest dollar in this case, okay? So that is the profit that I'm going to turn if I am going to produce this many 19-inch sets and this many 21-inch sets. So the question is, are we done, right? We found the critical point, and we have sort of reasoned with ourselves that it's a maximum. You can actually prove that it's a maximum. I urge you to go ahead and try and do that yourself. But the question is this enough, right? Is this actually the answer to the question that we set out to solve, right? How many should we actually sell? Well, the answer is no. We haven't completed the problem yet. Now, if you think back what you do in a single variable problem, you are going to check inside of your closed interval, and then you're going to check the endpoints, right? So if somebody tells you to maximize a function over a closed interval, you always have to check the critical points and the endpoints. Now in our case, we have to check the endpoints. Now those endpoints, so if we sort of draw the real plane here, we have checked everywhere inside of here, if this is S and this is T, but we have not checked on this line and on this line, right? Remember, these are perfectly valid. If a maximum occurred along one of those lines, it would say just produce one of the types of TVs, not both of them. So this is the subtlety that one encounters, and this is where, complex geometries can become a real burden. So in our case, let's check on this boundary first. So let's check S equal to 0. Now we've got a profit function that looks like this. Okay, so again, we want to maximize the profit function along the S equal to 0 line. And this thing is going to be negative 0.01 t squared, and then plus 174t, and minus 400,000. So all that I did to get this is I took my profit function down here and I set S equal to 0. Okay, so that's not too bad. Now I get a nice little quadratic negative leading value. That means whatever critical point I find is going to be a maximum in this case. But now this is really just a single variable optimization problem, right? You could do this. Just follow the previous 2 lectures. So in this case, this thing has a maximum. So a max at t is equal to 31,200. Okay, so you want to make 31,000 of the 21-inch TVs in order to maximize yourself whenever you're not selling any of the 19-inch TVs. Okay, so how did I get that? Take the derivative, set it equal to 0. But in this case, this gives a profit of $900. Again, rounded to the nearest dollar. So that means that if you produce no 19-inch TVs and 31,000 21-inch TVs, you're going to turn a profit of $356,900. That is less than the maximum that we found previously when you're producing both of the 19 and 21-inch TVs. So that rules out this line right here for us. It says that the maximum is still valid inside of the interior here. It's not happening along that boundary of our set. Now, you can actually repeat this to set t equal to 0. So you would set t equal to 0 and have a function just p of s, and you would maximize that thing over s, and that would give you the number of 19-inch units to produce if you're not producing any of the 21-inch units. And in that case, you can similarly find that that maximal profit you can produce there is less than if you're producing them both together. And so therefore, we can answer the question. So therefore, we should manufacture. So manufacture Well, we want to manufacture 4,735 of the 19-inch. And 7,043 of the 21-inch to maximize profit at this profit about a little over $500,000 in profit if you're doing this as the company. Okay, just like what we did with single variable optimization, now we can perform a sensitivity analysis. So what we would like to do is interrogate the sensitivity of our model with respect to some of the parameters that we had in. Now, the parameter that I'm going to use for illustration here is the price elasticity of the 19-inch TVs. That was the value that the price of the TVs decreased by after you sell one. Now you'll remember, maybe from your notes that you're taking, this is about 1 cent. So let's actually introduce that as a parameter into our system. So this means that my profit function, this is the same profit function that I used previously. The only difference is that it's going to be 339 minus a parameter times s. Remember, this was 0.01 previously, minus 0.003 t, and then this is all times s, plus 399 minus 0.004 s minus 0.01 t, and then minus 400,000. So it's a beast of an equation to write out, but just beyond looking ugly, it's really not that bad. Again, remember, it's just quadratic in S and T, okay? So I have it all the way across the top here, but what I really want to emphasize to you is this is a parameter now. Okay, so again, what I'd like to know is, okay, maybe I estimated this thing being 0.01, so losing a cent every time I sell one of these things. Maybe I'm off by a little bit, right? What if it loses actually? What if it's better to lose maybe 0.011 cents, right? So what if I'm off by 1%? Well, let's take a look at what happens. In this case, we can solve again. So let's solve the gradient of p equal to 0. Right? We can do this. We can compute these gradients. Let's actually just go ahead and write up what those gradients are. In this case now, they're going to be functions of your parameter a. So your solutions are also going to be functions of the parameter a. So here, minus 0.007 t. And I want that equal to 0. Similarly, take that profit function, derivative with respect to t in this case, 174, and then 0.007 s minus 0.02 t. So nothing really that different from the previous part of this lecture. The only thing is, I've got this parameter here as well, okay? So that means that my solutions are going to be functions of the parameter as well. So this is a system of linear equations. Again, I just want to solve for s and t, nothing fancy. So in this case, I can get s is equal to 1,662,000. I'm going to write it as the perfect fraction just so that it's a little easier to interpret. 40,000 a minus 49. Notice it depends on the parameter now. And now 8,700 minus $500,000-ish. So you can plug this thing into, maybe Wolfram Alpha or whatever you like to use, whatever computational aid you think might be helpful here. That's entirely up to you. But nonetheless, this is what you get for your solutions. And in particular, these things come out to be functions of your parameter A. Now again, I would like to compute the sensitivity with respect to this parameter. So first thing I would like to know is maybe what is the sensitivity of the number of 19-inch sets that I should produce, right? Is it going to go up or down? If I'm a little bit off on this A, is that going to cause a wild change in my number of 19-inch TVs that I produce? Well, let's take a look at this. So first thing, if you remember your sensitivity formula, the first thing I'm going to need is a derivative of S with respect to A. And in particular, that is the solution, the number that I need to produce as a function of A. So in this case, this is going to get, the numbers are starting to look huge, but I mean, aside from big numbers, it's not a big deal. So we're at this huge number here. But then that's divided by 40,000 A minus 49 squared, right? So all I did was took a derivative, right? Again, if you want to just plug it into Wolfram alpha, that's fine with me. The only reason that this is so big on the top is the 40,000 being multiplied into something that's already 1 million. Okay, so then what I could do is I could evaluate at A equal to 0.01. That was the value that I used in the first half of this lecture whenever I was computing the maximal profit. And so in this case, so ds dA at A equal to 0.01, this is going to give me negative. I'm going to keep it as a fraction again for a second, just so that it's a little easier to write or a little easier to look at. 0, 0, 0, 0 divided by 41,067. So I like to use whole numbers. I mean, it's up to you. If you want to use decimals, that's perfectly okay. But for now, if I don't have to use decimals, I'm not going to. But what this really means is my sensitivity of the number of 19-inch TVs produced as a function of this price elasticity, A. Well, remember, this thing is equal to, so I've got ds by dA times A over S. In this case now, evaluating all of this at A equal to 0.01, this is going to give me this big, ugly thing right here. Right, so that's there, divided by 41,067. And then I've got A, that's 0.01. And my S, that was from the previous half of this lecture. I computed this, so I was somewhere 555,000 over 117, right? And this thing is about minus 1.1. So what does that really tell you? It tells us that for every 1% of change in the value in this parameter A from 0.01, you are going to produce 1.1% less of the 19-inch TVs, okay? That's what that's telling you. So for example, if you go up by 1% in this thing, you should produce about 1% less. So these things, I mean, it's not a huge change. So making a small change in A, you're not going to lose out a whole lot by producing, this 4,000 of them. Okay, same thing for T. Okay, so I'm going to sort of skip all of the steps because it's exactly the same thing. You're going to compute the derivative of T with respect to A. That's taking the derivative of this thing right here. Then you're going to evaluate it at A equal to 0.01. You're going to get a nice elasticity computation of 0.27. So in this case, This is about a 2.7% increase in the number of 21-inch sets that you need to produce here. Okay, so what I really want you to notice is the negative value here and the positive value here. And in this now tells us that if I am going to increase my value of A, my price elasticity, by 1%, then I'm going to produce less of the 19 inches and more of the 21 inches. Now, I could do this even more, right? I could do this for my profit. So does my profit go up or down, right? And how much does it change by if I increase A by 1%? Well, first thing, so now for the profit, now my profit function, is now a function of A as well, right? So I'm going to evaluate my profit at my best production levels, S and T. So that means that whenever I want to take a derivative of D with respect to A, or sorry, P with respect to A, that means that I have to take a total derivative, right? I've got to do some chain rule applications here. First, this would be the derivative of P with respect to S times the derivative of S with respect to A. Then it would be the derivative of P with respect to T times the derivative of T with respect to A. Then it would be just the partial derivative with respect to A. Okay, so maybe if you were just starting out on this problem, you maybe didn't think a whole lot about that aspect of it. But fortunately for you, if you did forget that part, it's okay, right? Because what was the whole purpose? Where did these things come from? They came from setting the partial derivatives equal to 0. So that's 0, and that's 0. And this thing is just equal to the partial of P with respect to A, which is just this term right here. You take a derivative with respect to A, you get minus S squared, right? So we're going a little bit down the rabbit hole, right? Don't get too confused here. You might have to zoom out for a second. But we're doing a little bit of calculus on the fly. And so what this means is that my sensitivity of my profit with respect to changes in A, well, if I wanted to do this at A is equal to 0.01, this would be negative, and then S squared, which S is evaluated at A equal to 0.01, so that's this value right here. So let's write it all out. Sorry, 554,000 over 117 squared, and then times 0.01 over, and in this case, it's going to be over the profit. So this is going to be 21,592,000. So I'm writing this all in terms of fractions again, but all this is the optimal profit that we just computed. So maybe I'll make a little note of that for you. P. And in this case, this is somewhere around negative 0.4. So what that means is that if I take even like a 10% change in this price elasticity A, right? If I got it wrong, but I still worked at the production levels that I figured out for A equal to 0.01, I would be off by about 0.4%, right? My profit would go down by about 0.4%. So I'm not really missing a whole lot, right? That's a good thing. We want these numbers to be small. If these sensitivity values are big, right? So in our case, we have negative 0.04, 0.27, and minus 1.1. These are all really small numbers. But if those numbers were huge, right? If one was maybe 100, that's a very bad thing, right? Because that tells us that small swings in the parameter that we're interested in my case, it was the price elasticity A, well, small swings in that would be dramatic consequences. So of course, this problem is very, very nice. It's extremely robust. It says we can make mistakes, we can be off a little bit and still not make huge profit losses or not be, producing way too many or way too few of these TVs that we're not going to sell them. So this is a robustness computation that we're doing with the sensitivity here. And what I really want to remind you of is the sensitivity analysis is exactly the same as it was in the single variable optimization problems. The only difference is that we've got some partial derivatives now. That's the only thing that changed.